Good afternoon, everybody. This is Steve Wilson at the State Water Survey, and welcome to our webinar today on Groundwater and Well Construction 101. Want to mention that the private well class, which is our program here at the University of Illinois, is partnered with RCAP, the Rural Community Assistance Partnership, with funding through the US EPA for technical assistance and training for private well owners. Again, this webinar is part of a national program implemented through RCAP. Kind of the story there is we're kind of the online portion, or a lot of the online portion of this overall program, but RCAP itself has 6 regional affiliates and staff at each of those affiliates who are working with private well owners all over the country in person, including doing assessments for their wells and offering some assistance with water sampling. The materials today, especially today, do follow the information in our private well class, which this is not the class. The private well class is a 10-lesson class. You sign up for online, and it sends you an email once a week for 10 weeks with an attached PDF, and that PDF make up the 10 lessons that are actually the class. And if you haven't taken the class and you've only participated in the webinars, I highly encourage you to sign up on privatewellclass.org for the class lessons. There's much more detail. They're PDFs you can keep and use when you need them. They provide, again, more detail than we can certainly provide in an hour and a half or so today. One thing I want to mention that we did get a lot of questions in advance from everyone who registered, and we'll answer some of those. We obviously can't answer them all. But if there's anything today that you have questions about as we go through, there'll be time at the end. We'll stay and answer questions as long as you're willing to stick around as well. And you can put those in the question box or the chat box on your GoToWebinar screen. And Katie Buckley's monitoring that, and we'll put all those together and we'll pull them up on the screen at the end. So if you have questions today, again, you can put them in the question box or the chat box in your GoToWebinar window. Okay, if you are here today because of you get CE credit, continuing education credit through NEHA or Illinois as an Illinois LEHP. A little information, the NEHA credentialing schedule is 2 years. You can't take the same course with the same content only once every credentialing cycle. So for instance, if you just started your credentialing cycle the first of this month, it ended on 9/30, then if you do the webinar today, you can't take it again until after 10/1/25. So I put in the lower right corner the other times we've offered the same webinar in the last 2 years. And what we can provide, and it's also on the handouts page, is the CE completion record for this certificate of attendance. We can provide a copy of the slide deck, and you can work with us by emailing us at info@privatewellclass.org to get all that taken care of. And I'll just mention, we are a small shop. There's not many of us on this program, and so we get a lot of CE requests, so be patient. It takes a little time for us to work through all of that and confirm that folks are actually here. Our rule is 90% of the webinar you need to be on and active to actually get credit for it. Okay, so today my name is Steve Wilson. I'm a groundwater hydrologist here at the survey, and Katie Buckley is our water resources outreach specialist who is taking your questions, set up all the questions that we've received in advance. We also had question help from Walt Kelly, who's the head of our groundwater section. And I didn't remember to put in here, we also have an EHP who works for us now, Sally Dolan, who's here and listening in. I'm not sure you'll hear her voice today, but she is here and participating in our program and does a lot to help us overall with our program. First thing is to do a poll question. This helps us understand who our audience is. It also helps us provide information to our sponsor who requests this information, and it also tells us that you're actively listening and participating in the webinar. And so if you would, Katie's going to open the poll question. She maybe already did. And then please fill that out.
The poll's open. We just want to know what best describes you as a participant on our webinar today. So just select the one that most closely resembles your profession or title. And we'll give everybody about 30 seconds or so to fill that out. We have 85% that have voted. Just a few more moments. All right, I'm going to go ahead and close the poll. We have 89% have submitted their votes, and then I will share the results. All right, so it looks like half of you are with a regulatory agency and some well owners on here as well, and quite a few health professionals. All right, Steve, back to you.
Hey, thanks. All right. So RCAP, the Rural Community Assistance Partnership, the reason, especially if you're a professional working with well owners, you need to know about RCAP and work with them, is they have a dedicated staff. They have in each of the 6 regions. These are the 6 regional affiliates. You may know them by another name like Communities Unlimited or Great Lakes Community Action Partnership. We're in Illinois, so the region that we're involved in is Great Lakes. But whatever state you're in, there's an RCAP region and staff to support you. They do a lot of all the boots on the ground work. Like I mentioned, we do well assessments. We worked with a group of professionals about 6 years ago or 7 years ago to develop an assessment tool. It's like a vulnerability assessment for a private well, and that's available. They will come out to a well owner's home free of charge, talk to them, work with them about, and ask questions related to, what's near their well. Is there a well log? They'll look it up if they can find it. What kind of pipes they have they tested or treated their well? All these things put together in one place, which gets handed back to the well owner. So they have a record of all this information, as well as then they can provide some best practices, like, you should sample for coliform nitrate annually. And, it's probably not a great idea to, maybe they have a bad well cap. That seems to be a much more common problem as far as the physical well itself is a improperly sealed well as far as a well cap, things like that. They also will work with you to put on workshops. They give a lot of presentations. I just talked to the MAP, Midwest Assistance Program lead yesterday, and he's gives a talk every year at the Iowa Well Drillers Association meeting. And we were just discussing some of those things. And so if you would like to put on a workshop for well owners, or even if you're some community group or whatever, there's staff who will come and help you advertise it, provide speakers, help you find other speakers like drillers or whoever, or extension, and work with you and be a partner. That's the goal of our program, and it's all free, right? It's funded through US EPA. So all the work we do is free of charge to well owners and those that we work with, just like today's webinar is free for you all. If you want to get in touch with one of the RCAP regions, their information's up here, but you can also email us, and I will gladly put you in touch with the right person. The one thing I get a fair number of referrals for is well owners who contact us wanting an assessment. I just forward that information to the regional lead for the private well program in the proper region. They will get in touch with you and try to set that up. I just show the front page of the assessment tool. It doesn't really show a whole lot. There are 18 sections though, and who the assessor is, that would be like one of us, and then who the participant is, whether it's the owner or a renter or what it might be. And then it starts going through sections on a lot of things related to the well and water use, as I mentioned. And so it's like a sanitary survey for those of you that are familiar with those. Those are kind of a vulnerability assessment done on a community water supply every 3 years per the Safe Drinking Water Act. But this is voluntary and it doesn't go to anybody else. And it's really meant to help well owners understand what their risks might be. Some have a lot of wherewithal. Some well owners do and understand like what a improper sealed well cap might look like. Others really don't have an idea of that and need someone who can show them and give them good advice. And that's what that's about. It's a chance to educate well owners. Every well is different. In my experience, every time you go to somebody's home to look at a well or they have a problem and you're trying to help them solve it with their well, there's something unique either about their homestead or their well itself, or what activities are going on there, where they're at on the landscape. It's rare that you find two wells that you could basically call identical in all aspects. So in addition to that, then there's a chance to promote best practices. So we have a list of things that we believe well owners should do regularly, including testing, and it's a chance to put all that down on paper and get that in front of the well owner. And it helps not only encourage communication, but also eliminate miscommunication or misconceptions about things. Like, we recommend that well owners contact their local or county health department. You'd be surprised at how many well owners tell us, well, I don't want to call them because they might condemn my well or tell me I can't drink the water. There are very, very few places where that's actually can occur. In most states, the local health folks don't have that authority. There are a few local jurisdictions in the Northeast where they do. And what I tell folks there is call your health department first and just ask them what authority they have. But, what we encourage well owners to do is especially if you test your water and you need help interpreting the results of your water sample, your county health department or local health districts is one of your best bets for that. Okay, so the assessment program, as I mentioned, so RCAP's done over 3,600 of these around the country, which is amazing because it's several hours of work. They've also led workshops where we've trained others to actually conduct those assessments. And, again, the idea is we're a national program and we're trying to reach all the way down to a well owner in a given jurisdiction. And the best way to do that are through these webinars where it's kind of a train the trainer, if you will. And also it gets us in front of a lot of local health folks who then, when something comes up, may call us or may want to work with us or partner with us, or may have a program and not realize that, we're available to provide support to what they're already doing. And so, our goal is, again, to develop those partnerships and support what you all are doing at the state and local level. So we're at the State Water Survey, which most folks outside of Illinois have never heard of. But it's very much like a state geological survey. Illinois just happens to have two separate surveys, a geological survey and a water survey. Ours was formed in 1895 because of cholera and typhoid outbreaks and some of the waterborne diseases that were being discovered at the time. And so we have a 128-year history of working with water and in public health. It's actually, we're in a really unique spot because we not only do outreach and education, we also do research, especially applied research, and we provide technical support for communities and well owners and others who are dealing with water issues. We have the state climatologists. We do a lot of kind of wild weather work, if you will, and look at some of those things, global climate models and all that, as well as, a lot of surface water and lake type efforts from our different group. There's over 100 of us here. We all do applied research as well as those other things, including programs like this one, which is actually a lot of fun and hopefully helpful to more folks. So we have all these archives with data going back to 1895, and we found these old glass plates. This is a glass plate up in the top part of that, and I blew that up. This is back in 1913, trying to figure out where the source was for all the cases of typhoid in Rockford, Illinois. There were over 115, I think, in the end. And one of the things they looked at was milk. Several times milk ended up being the culprit in different cases. And here they followed this gentleman's dairy route and saw that only 8 of the cases were actually part of that. So they decided that wasn't the case. This glass plate happened to be broken, but it tells a great story. And so, yeah, there's 1,500 of these. We've only gone through a few hundred of them so far, but it's pretty cool to go back and see how things were done. If you're a well driller, hopefully you can appreciate what kind of work this was. These are 10-foot sections of pipe. This is for the U of I's well number 11, which I think this is in 1923, maybe. I can't remember the date. But all the spacers were welded, all the rivets were put in place. This was a monumental task compared to the technology and equipment we have today. Not that well drilling isn't still a heck of a lot of work, because it is, but you know, hats off to these folks for the effort it took to put in a well back in these times. Just, I mean, honestly, it's no different than some of the buildings we see that are 100 years old, and you look at the architecture and the craftsmanship that went into some of that. It's just amazing what was done. Yeah, this is they're drilling this well for Weldon, Illinois. It's a small community in central Illinois. That's the drill rig of the day. So I find all this really fascinating, being a lifelong career in water. So back to our lessons here. If you're a well owner, there's really these 3 things to remember. They're not regulated. And once they're installed and once they've met construction code and been approved by the local regulatory group, if that's being done, then at that point, it's really up to the well owner to be sure your water's safe and that the system's maintained. You're on your own. You are the water operator for a very small water system. And water can be the best tasting and safest in the world, but we also have contaminants like arsenic that are colorless, odorless, and have no taste. So you don't know what's in your water unless you test it. And so many people believe, because we tell folks you need to test annually for coliform and nitrate, that if you test for those things and it's clear and they're not found, that means your water's safe to drink. It doesn't. And I'll get into that more, but you also need to test for inorganics and metals like arsenic to understand what might be going on. Those are natural occurring contaminants in the Earth's crust. And so they're just there, and you don't know whether they're in your well unless you actually test for it. I grew up on an old dug well that was only 14 foot deep. Now I live in town. And I keep forgetting to update this slide. I've got a 12-year-old daughter, so it's no longer $40 or $50 a month. It's much more like 70 or 80. But that's what I pay every month for our community water supply. And that is a cost for me to have water and all the other 150,000 residents to have water that's safe, that's been sampled, that all the pipe and infrastructure are maintained, so that when I turn on my tap, I always have water pressure and I know my water is safe to drink. As a private well owner, those things are your responsibility. You have to maintain your system. You have to make sure that you have water pressure. You should test to make sure the water, meets safety criteria, all those things. What our program really is about you being aware as a well owner. You need to know if you have a well log. If you don't, you can try to find it with your state agency or maybe your county or local health district. But what's on your log is important, and we'll go through some examples today. But where your pump's at, if it has a screen or not, what is the total depth, how much casing is there? All those things matter when you're talking about water quality and especially protection from surface contamination. And so understanding those things can give you peace of mind and help you understand whether there's a risk or not. Are there natural occurring contaminants in your area? We know in Illinois what areas have arsenic. And I talk about arsenic a lot because I spent 10 years researching arsenic in Illinois groundwater. And so we know where the mineralogy is such that there's arsenic in groundwater, which counties have it more than others, which counties where there's none. And so there's likely a state agency in your state that also knows those things. And so if you're curious, contact your USGS or State Geological Survey, or if you even look up water quality, in my state, whatever that might be in Google, it may be a DEQ or a DNR or a Department of Public Health. Like in Minnesota, you would call the Minnesota Department of Public Health. They can get you to information about where they know there's certain contaminants, natural occurring or otherwise. And so by going through all this information and taking our class, the idea is it helps you as a well owner learn what are the right questions, or even to ask better questions because you know all the basics, and then where you can find local information. We get questions that are very specific about a certain location, and if it's not in Illinois, I probably don't know the answer. I can find the answer, and you can too. And, knowing who to contact is really the key to all that. So that's the idea. Everyone needs to be inquisitive. You need to have a certain healthy, I won't say healthy fear, but healthy understanding of what could happen with your well. Many times groundwater is perfectly safe and your well water is perfectly fine, but you don't know if you aren't proactive and take care of it. And then lastly, again, sample your well, sample your water. If you don't do that, you're really not sure. So we're going to do today's groundwater and wells kind of a 101. So we're going to talk about geology and well types and the geology behind those different well types. So two concepts that are really important. One of those is porosity. So porosity is a measure of the space between all the grains of geologic material. So in a sand and gravel aquifer, this is all sand and gravel. That box is a volume. You can see that water can run through. The image on the right, those are sand grains and water's moving through that sand. So the question is, how much, if that sand were dry and there were no water in it, how much pore space would there be? And that's a measure of how much water there might be. So, let me go back. So for instance, in a uniform sand where most of the grains are all round and the same size, the porosity can be as much as 30%, which means if I have 100 feet thick sand and gravel aquifer that's full of water, if I took all the sand away, there'd still be 30 feet of water. And that is a boatload of water. There's just no question there. When you think about river bottoms where it's all sandy alluvial material along like the Mississippi or any other major river system, you see a lot of irrigation. Those wells are pumping 1,500 gallons a minute and sometimes more. And that's because the sand and gravel aquifers there have a lot of water available and it can move through the sand quickly and keep the well going. Whereas if, water couldn't move through, there wasn't much pore space, that would be a problem. And this is sand and gravel. And this is how it works in unconsolidated material, which is not bedrock, right? It's all the material, the sand, silt, and clay that's on top of bedrock. When you get into bedrock, it's a fractured system. If I had a big piece of rock sitting here, it doesn't have any pore space. There's no water running through it. Water goes through the fractures in the rock and the crevices. And so the size of those fractures and how interconnected they are, that's what dictates how much water is available to a well. If you drilled a well in the middle of this picture and you hit 4 or 5 of these fractures, you would likely then have ample water. And we see bedrock aquifers that are used for irrigation as well, where there's large fractures that are storing water and they're very well interconnected. We also see like on the western slope of the Rockies where it's all granite, which the porosity here is measured by the volume of the fracture space, which can still be fairly high, right? Like on this picture, that's probably 15% maybe, or 10. But you get in granite and your porosity and the amount of fracture space may be 1% or less. And so it's much more difficult to get a good water supply or even to get a well that has water in that sort of environment. And so really the fractures dictate what's going on with a bedrock well. So just here's some examples. This is from the University of Arizona, manual they put together. But it's different. On the top are all the unconsolidated sands. Basically, it's porous. It can either be well sorted, which means it's more uniform, or poorly sorted, which means it's much more different sizes of sand and gravel put together. This diagram actually doesn't show it as well, but that blue, if you take that to be water, those should be flipped, because the poorly sorted sand looks like it has more water available, and that's actually not the case, because some of the smaller particles fill the pore spaces between the larger ones. And when you have more different sizes all together mixed up, you actually have less porosity. So in a fractured rock, as I mentioned, you can have granite where the fractures are small and not as connected, or you think about Southern Illinois, Indiana, Kentucky, Tennessee, where we have a lot of caves, and it's because water readily dissolves this limestone, and that creates fractures and then caves and large crevices where water can be stored. So there's two issues here. One, there may be a lot of water available in a more cavernous type limestone, but it also means there's likely sources from the surface where the water's running directly into these deeper channels, which means they're more contaminated. And one example of that is karst. You've heard the term karst, or maybe you haven't, but karst geology is where you have sinkholes at the surface. You have rainwater runs straight into the bedrock from the ground, from the surface. And in those cases, more times than not, it's contaminated, especially with bacteria. We have karst geology in Pike County, Illinois, and at their health department, county health department, about 80% of the private well samples come back positive for coliform E. coli. And so it's, there's more water available, but it's also contaminated from the surface. And so anything that's going on there, livestock or other activities at the surface, are going to affect water quality. So the other factor besides porosity, which is the space available for water to be stored, is permeability, which is kind of a measure of velocity. It's not quite the same thing, but very similar. And for our sake and our terms, we can call it that. So the permeability depends on the size of the grains. If you just look on the left side, we have gravel, the largest particles, then sand, and then we get to silt and clay, which are really small particles. So the interesting thing is clay can have a porosity of nearly 30%, just like sand and gravel do, but the particles are so small that water has to take this convoluted path to get through it. So silt and clay are both much less permeable, which means water can't flow through it nearly as fast. And so if you start pumping a well and it's finished in clay and silt, it's going to go dry much quicker, because water can't flow through those materials back into the well to keep enough water in it for pumping. So a lot of times we see when you don't have good sand or gravel or highly permeable materials, you'll put in a large diameter bored well, which is really like a large storage tank. And so water can seep in slowly because the water's there, it just can't get into the well very fast. And so by having a large diameter, you store it, so when you have water available when you need it, and then like overnight, it can fill back in. So water can move as fast in a gravel as 3,000 feet a day, and that's partially dependent on the head difference, or the water level difference from point A to point B, which kind of drives water flow. And when I say that, a good example would be if I had a table sitting here and I poured water on one end and had a pool of water, if I lift up the end of the table, water runs downhill, right? And how fast it runs downhill is dependent on all the resistance it meets from all the grains there and stuff. So when you have differences in water level, that drives water to flow from the high area to the low area as it goes. And then on the bedrock side, well, I guess I should mention too, so clay is relatively permeable or can be impermeable. 1 foot in 10,000 years is pretty slow, right? So it's not really going to help you with your well if, that's why you don't finish a well in clay typically. Same thing on the other side, it's the bedrock side. Shale is basically cemented clay, And so that's why, unless it's fractured and there's cracks in it where water can flow straight through the fractures, it's very slow. So it really depends. A typical limestone, it can also be fairly fast. And again, that's flowing through those fractures, and they call solution cavities, which are where the water has eroded the rock and made the hole bigger, so to speak. But it's through the fractures and fissures in the rock. So it all matters where you live, what's the geology at your location. It's not something that you can do a lot about. And so, yeah, some people have water and some just don't. And this is just another example. So I liken this to a tank full of, upper left sand and gravel. If you could put water evenly over the top, it would run through the sand and make a wetting front like the one that's shown on the upper left. Crystalline bedrock's the same as granite. It's an example of granite. And you can see water will flow into those fractures, but they're not connected. They're very small. And so if you put a well in some of those places, you might not have any water. And others, you may just have a little. Where dolomite, they're showing this as an example, more like a brick structure. And so it's flowing between, those are all cracks in the rock. And so how water moves through that system is going to depend on where the fractures are. And the bottom right is a little more complicated, which is the reality. In the real world, you have different layers. You have sandstone, dolomite, shale, all kinds of different things. And it's also not flat. Those are angled deposits typically. So where, as an example, in about 100 miles west of Chicago, you can hit a bedrock aquifer that's less than 100 feet deep. And that same bedrock aquifer is at over 1,500 feet in the Chicago area. So over 100 miles, the angle of that goes from 100 feet below land surface to 1,500. And that's just the way the earth was formed. And so the people out in the Rockford area in Illinois, for instance, have to go a lot less deep to get to their water supply than the folks in the Chicago area that want to use that deep sandstone. This is from the Iowa Department of Natural Resources on one of the documents they have related to wells. This is a good example of what things really look like, at least in the upper Midwest, where you do have glacial drift. So we had glaciation in most of Illinois. Obviously, there's a lot of areas in other parts of the country that don't have this glacial drift. You take that off, you still have limestone at the surface. But if you do, you have sand and gravel aquifers. And that's what this is showing. So there's two wells up here in the shallow sand and gravels. A lot of those associated with rivers, which is what that diagram's showing at the top. It's a cross section through a river. They can also just be buried things of sand. They look like that bowl shape because they go into the paper, into the screen and towards us longitudinally like a big tube of sand. And that's because when the glaciers melted, preferential paths for all that water flow formed all the rivers and the sands that are around those rivers from all that melting ice. And then when you get down into bedrock, you have shales, which are not aquifers, a confining layer, and then you have the other areas are considered aquifers, sandstones and limestones. And this is a pretty good representation of what you might see. So depending on where you drill, you might have one or two sand and gravel options and also two or more bedrock options for where to put your well. Obviously, you're not going to drill into the deepest sandstone unless there's a reason to do that. The reasons would be one, it's the only aquifer that would provide the volume of water you need. So maybe a private well, maybe in the upper limestone for a home, but for a large community that has 6 wells that all pump 1,000 gallons a minute, they may need to be in the deep sandstone to get that much water without dewatering one of the shallow aquifers. And so the other reason would be water quality. Maybe the upper limestone has some other constituent in it that the deeper limestone or sandstone do not, and that may affect the decision whether or not to use which aquifer. And I know in Wisconsin, there's a bedrock unit that is very high in arsenic. You know, the standard is 10 parts per billion, and I think it has in the thousands of parts per billion. And so their state legislature, as part of their drinking water rules and well construction rules, require you to actually seal off that unit if you want to go below it, or not to drill, to only drill above it, so that there's no chance of that highly contaminated water being part of a well. Okay. I apologize. I meant to put in I have a new figure for this and I forgot to use it. But this is showing kind of the dynamics of how water flows as part of the hydrologic cycle. A lot of folks forget about the groundwater portion of that. They think, well, it rains, it runs off, it gets into a stream, it goes to a river, then the ocean, then it evaporates and starts all over again. But some of that water actually infiltrates into the ground and forms a water table near the surface. Some of that will run off and seep into the side, you know, like it shows on the side of the hill, there's a seep, but some of it keeps going. And it may take a long time, thousands of years, but eventually water, some of that gets down into even the very deep aquifer there that says a lower aquifer that's confined. It can move through that aquitard that runs across the screen, but very slowly. And so, you know, there's ways to determine the age of water using isotopes. And so we've dated water that's, you know, more than 50,000 years old that's in the ground. Eventually that will come out somewhere. It's still part of the hydrologic cycle. It's just got to find its discharge point and make its way through all these different materials. In other areas, you know, water that infiltrates into the ground right by the stream may only be in an aquifer for a couple days, and then it's back in the surface water as part of the system. So it's really complicated. It depends on the geology again, but yeah, it's interesting how some of that all occurs and how water can, it will eventually make its way to the surface again, just sometimes it takes a long time. So as far as aquifers and wells, you know, you can only put a well in where you have the proper geology for that well type. So when you don't have a real aquifer, or in a lot of cases, the very old wells we run across, like the one I grew up on was hand dug in 1933 by my grandfather, then they're dug or bored. And again, those are large diameter, 3-foot diameter, or sometimes much larger, that are meant to store water. But for drilled wells, they can either be drilled into a sand and gravel aquifer or into a bedrock or consolidated rock aquifer. And so like we showed with the Iowa diagram, in some cases you might have choices. You know, you might put one in sand and gravel, or maybe you're the unfortunate person where you drill, you know, your neighbor has a well that's only 110 feet deep and it's in sand and gravel, and your location a mile away, that sand doesn't exist. And so you have to drill into bedrock and you have a 300-foot well. Those things happen because geology is complicated. How it was all laid down originally by Mother Nature is one of the great mysteries, as far as whenever you're trying to map all these things and know where your water is. And so you may have 3 or 4 choices, or you may have none. And so, but we have enough information in general in the United States that our state geological surveys and USGS offices typically have good information, along with some of those other state agencies I mentioned, like DNR or DEQ or departments of public health, to know where there's a good water supply and what the water quality may be. So dug and bored wells, these are all examples of dug and bored wells. The one at the top left is an old hand dug well that, you know, this well's probably I have no idea, it could be 100 years old. But they're still using it at the farmstead that's up over the hill there. The well's down on the side slope, probably because they couldn't get enough water up by the house. And but you know, this is a poor situation. Having 2x10s and covered by tin and concrete blocks and rocks isn't the best way to seal your well. Mice, snakes, maybe even larger critters, if one of those boards is missing, can get in the well, fall in and die and decompose in there, and that's your drinking water. Ironically, this is a pasture for cattle. And the reason those posts look so worn down, it's because they're the best scratching posts in the whole pasture. So the cows come over and they'll scratch on those posts and then do their business there. And that's all infiltrating. You can see how wet and muddy it looks here on the right side of that picture. And all that's seeping into the ground right there. A very unsafe well, and you'd be surprised at how many of these still exist in the United States. A lot. Matter of fact, the well that I grew up on is still in use. The picture on the right is a 3-foot concrete tile well. It's also a large diameter well, but it's called bored. So there's a boring machine, which I'll show you in a second, that drilled that hole 3.5 foot, and then they use 3-foot concrete tile like you'd have under a road horizontally. They place it vertically in the well, in the borehole, and where those 4-foot sections meet, there's a male end and a female end, and they fit together. It's not sealed, so water can seep through those 4-foot sections where the joint is. And so depending on the number, how deep you went, water can seep in from the water table and fill that well up slowly. And so typically you drill a 3.5 foot hole for the 3-inch tile. So the area around it, you'd put sand to provide a little more volume or gravel, and then you'd seal it near the surface. But if it's not, if the outside isn't sealed near the surface, then the first seam, if you will, on this particular picture would be, if you say that's a foot above land surface, that first piece of tile, then 3 foot down there's a seam or a section joint. And so water can seep in at 3 feet, and that's not safe. It's just not. Shallow infiltration, if you're using yard chemicals to treat your yard, there's certainly, I don't see a dandelion in sight. Those things can get into your well then. And the one on the bottom left is really like the one on the right. It's just that the 3-foot concrete pad on top starts 10 feet down, and there's a hole in that concrete pad for this well casing, so that it looks like a well, and then you can fill up that upper 10 feet around the well with less permeable material, so that it gives more protection to the area where water's seeping in the well. And here's what those look like. The one on the left is a diagram that where the concrete slab's on top. This isn't accurate because it shows that the pipe comes out of the top in the middle. These days, that goes to the house 3 or 4 feet below land surface, and they'll have a 90-degree bend there and a pitless adapter or some other way to turn that in the house. There's no reason to have that come out the top. And then the one on the right has the concrete pad 10 feet or more below land surface. And like I said, you can fill that in then with, this says clean earth fill, more of a clay fill, if you will, or even concrete, so that water's actually not coming in the well until that first seam below that, which looks to be about 14 feet. And that gives you a little more protection from the surface because water can't seep in right near the surface. And the example on the left, they put concrete around the outside of the well for the first 10 feet, which is proper construction in Illinois, so that water can't seep in that upper 10 feet. But a lot of the older wells, like the one I grew up on, is old hand brick with no cement around it or anything. So water can seep in at a few inches below land surface, which is just not safe. But like when my grandpa put our well in, he was looking to maximize the amount of water that would be available. So we actually put it at the base of a ravine, and so water could run in it all the time. But it was in a pasture, just like the one we looked at before, except it was all the way at the bottom of the hill. So sand and gravel wells. So the picture is of a well screen. That's a stainless steel wrapped well screen. There's little slots between there, a little space between those woven sections of stainless steel, and the size of those slots is determined when you drill the well based on the size of the sand grains. So if it's more coarse material, then you can have a wider slot. If it's fairly fine sand, you want to have a very narrow slot. The whole point of the screen is to let the water in and keep the sand out, right? And so how that looks in a diagram here is you can see there's a well screen and there's a pump inside. The blue inside the well is where the static water level is. There's a pitless adapter at 3 or 4 feet that allows the water to go to the left and run into the house. And then there's a drop pipe that you can pull the pump out if you need to. In this case, it's a submersible pump. So it's pretty simple. The key things here are that the casing is usually PVC or steel, and it's solid. There is no place for water to come in this well except at the well screen. And that's a good thing, because water can't seep in near the land surface, or there's no seam in the shallow unconsolidated material up there in the soil layer where water could seep in. And so it's more protective in that respect. And for any well, the amount of solid casing you have really matters before there's an opportunity for water to get in the well. And so, usually they're sized based on what you need. A irrigation well might be 12 inches, so it can have a bigger pump and pump a lot of water, where most home wells are between 4 and 6 inches in diameter. So that's really what's going on. This is a well log from Illinois, which I forgot to mention. The State Water Survey, one of our jobs is to house all the state's water well logs. So we have a file room with about 500,000 well logs, even though we have about 800,000 wells in use in Illinois, and that's actually good compared to many states. So as you look through this log, there's a lot of great information on here. It tells you about the pump. It's a 15 gallon per minute pump, which is actually a lot for a home well. Usually they're more like 5 or 10. It's set at 124 feet. I'm on the left side still. All the information for the driller and all those things. They grouted the well back up at the top there with bentonite to 192 feet, which means on the annulus outside the casing. So where they, if you're going to put in a 6-inch well, I guess this is a 5-inch well, you're probably drilling a 6 3/8 hole. So the area outside of the 5-inch casing where the borehole's still open, you fill that with grout, which is bentonite clay or cement, something that will not allow water to move through. And that protects it's called the annulus, and that protects the well from water seeping in along the outside of the well and getting into it. If we go to number 22, it shows that they use 210 feet of PVC. It starts 2 feet above land surface and goes to 208 feet below land surface. And then they put in a 4-foot screen that's slot size 12, which I believe that's 1200s, but don't quote me on that. But again, the slot size depends on the size of the sand grains as they drilled, and the driller makes that call typically when they're collecting samples as they come up with the water as they're drilling with the rig. And I say that the only rigs I've really worked on are either auger rigs or reverse mud rotary. And so we collected samples when they're coming up as they drill around the drill pipe. The 5-foot screen is stainless steel. And then number 23, as you move down, the water's from sand from 172 to 212. And you can see that on the log that's down below that. They also pumped it. The static water level is the water level when it's not pumping. So that's the natural groundwater level. It was 72 feet below land surface or below the casing. And so they pumped it with a 60 gallon per minute pump for 2 hours, and it dropped to 140. So the thing to note here is there's clay from 160 to 172, and yet the static water level was all the way up to 72 feet below land surface. That means that aquifer is under artesian pressure. So the water level came way above the top of the aquifer. The aquifer stopped at 172 feet. That's the top of it. And yet water level came up another 100 feet. And if you think about it, it's because of all the pressure from the ground, and also the aquifer is probably not flat. as it goes laterally, has a lateral extent in other directions, and somewhere else it may be at a higher elevation, and that's pushing that water in the well to come up to that level. Think of it like if you have a straw in a juice box, if you squeeze it, what happens? Water comes up the straw, and if you squeeze it hard enough, it comes out. And that's kind of the concept there. So anyway, they pumped it at 60 gallons a minute, which is way more than a home could ever use, and it only went to 140. So then when they put the actual pump in, if we go back to the left side, it says the pump capacity is 15 gallons a minute, and they set it at 124 feet. So that's not necessarily intuitive. They put it at 124 feet, even though the water level dropped to 140. Well, they're only pumping it at a quarter of the rate that they did when they did the test. So when you pump it less, the water level is not going to drop as much. The amount of drawdown is based on how hard you pump it. And so I'm sure the water level won't even be close to that 124 feet ever, as long as nothing else changes with the geology of the system. I don't think I missed anything else. It's a great record of what's going on. So this well owner will have a very good understanding of where the water's coming from. And the advantage here is that the only place water's coming in this well is from 208 to 214 feet below land, or 212 feet below land surface, nowhere else. So it's 208 feet from any surface contamination. So even if there were a spill or some kind of contamination near the well, as long as it's properly grouted and there's no pathway down to that 208 feet where the screen is, the water's not going to see that probably ever. It'd be very hard for any spill to get to 208 feet through this type of geology. So the difference is bedrock wells. Typically when you drill a bedrock well, again, there's no porosity, you don't have a screen. The only way to get water is through the fractures. And if you put casing over a fracture, then water can't get in the well. So what you typically do is you only put casing 10 to 20 feet into the bedrock, and then you keep, that's whenever you're finished, but you have drilled a much deeper hole. So in this example, if you look at the picture, it shows casing 10 to 20 feet into the rock, and then below that, there is no casing. The rock itself acts as the casing, and then the fractures are open to the same, basically the well's open to the same fractures in them that it hits. So that can be good and bad. So the water, if you have a lot of fractures, then there's going to be a lot of water available, and it's pulling from from whatever direction the fractures go, and that's also the bad thing. As an extreme example, let's say there was only one fracture, and that's where all the water came from. If you follow that fracture back off the screen somewhere, it may go close to the surface. And if it does, that means water from near the surface can get into that fracture, which means it can get into your well. So they can be influenced over a much larger area because fracture flow, there's a lot less volume in a given fracture, and so it's pulling from farther away. And also, there's no way to know where those fractures actually go. We don't have that kind of capability. And so there's always a chance that it goes to back towards the surface, or some other fracture it connects to that may go to the surface. That could be a problem. So as an example, I was working in New York a number of years ago, looking at some wells in upstate New York, and there were a number of wells that were 600 feet deep. But when you look at the log, some of them only had 15, 25, 30 feet of casing. So if a well has 30 feet of casing, that means anywhere below 30 feet in that well, water could get into the well if there's a fracture. And this is an area where bedrock was right at land surface. And we were actually there because there were a number of homes that had contaminated wells, and it turned out it's because of the geology, and that there were a lot of septic systems that were putting stuff straight into the aquifer. It was a really poor situation, unfortunately. But the depth of the well doesn't matter when you're talking about bedrock wells. It's much more important to understand how much casing there is. You know, if this well had a 600-foot well had 300 feet of casing, then no water could get in until 300 feet. That's one thing. But when you have, literally, there was a few of the older wells that had, you know, one had 12, one had 15 feet of casing, and that's it. I don't think that's allowed today, but some of these were put in well before well construction code in New York was developed. And so you have these old wells that can really be a risk. And so that's, you know, if you have a bedrock well, my point is you need to know how much casing you have to know, because anything below the casing means water can get in, and understanding that is a lot more important than knowing the total depth. And here's a bedrock log, also from Illinois. Yeah, and I guess I won't go over all the other rest of it, but you can see here, if you look at number 15, they used 179 feet of PVC and then 20 feet of black steel. And they did that because, you know, PVC is much easier to break. And when you seat the casing into the bedrock, which if you look down at number 18, they hit broken limestone at 189 or 187 feet. 2 feet of it, they called it broken, which means it's just really fractured and friable. And then limestone starts at 189. So they put a steel casing from 199, 10 feet into the rock to 10 feet above, and they connected PVC to that up to the surface because PVC is much cheaper than steel is, right? And so that's just a cost saving measure and shouldn't affect anything because you've got that seated with a good steel casing. But the well depth, if you keep going and look at the number 18, the well goes to 260. So if the steel stops at 199 and the well doesn't stop till 260, that means there's no casing from 199 to 260. And that again is taking advantage of all those fractures in the bedrock and the limestone. And so in this case, the static water level is 130 feet, which is well above the aquifer again. So it's also artesian. And then they pumped it at 25 gallons a minute for 2 hours and only dropped to 160. And so it's pretty good aquifer. There's a fair amount of water available. And again, they pumped it at twice the level of the pump they put in. They put a 12 gallon per minute pump, which I know someone asked about horsepower. You know, 12 gallon per minute pump, pumping 160 feet, it's probably 3/4 of a horsepower, maybe one. But a lot of wells for private homes, this actually is for a camp. A lot of private wells are half horsepower, unless, you know, for some reason, it really depends on how far you have to lift it and some of those things as well. But yeah, so again, this well log explains a lot, which is really handy. So moving on, you know, the whole purpose of our program is really to protect public health. And that is, you know, the number one focus, as well as source water protection. People can do a lot of things that might even impact an aquifer, especially on an old well. We see abandoned wells, for instance, that are not sealed, where someone will throw stuff into them because it makes a great garbage can that no one will ever see again. And so you may be contaminating the aquifer, and really understanding water quality is, you know, what it's about. And then those all stick together. They all are intertwined in the issues that need to be impressed upon folks who have a private well. They need to understand their water quality so they can protect their public health as well as protecting their water source. There's also a bunch of issues that make the news, right? When we have drought or flooding, you know, any kind of contamination issue. Right now it's PFAS. Before that it was lead. Terms like non-regulated drinking water, which private wells technically are non-regulated drinking water wells, but they're private wells, and a lot of people choose not to have the government or a state agency or anybody else dealing with their water supply. They want to deal with it themselves. And I mentioned boil orders because when we talk about well owner knowledge and education, I have water operators who will tell me they get a call anytime that they issue a boil order in their town, and that's usually because of a water main break. So when that happens, then they can't ensure that water's not seeping in from the ground into the water line. And so you have a boil order in case that does happen until it can get fixed. But it has no effect on the aquifer or anybody else's well if they're on a private well. And they'll get calls from people who live, like a mile out of town or half a mile out of town, asking them if they need to be worried about their well because they issued a boil order. It's just not a thing. And so those are great. All these issues in the news because they raise awareness and people are more interested in learning about their water supply. And so as someone who educates well owners, a lot of times these are an opportunity, but they're also not the real issue. What we found in our work with well owners, which for me it's been 30 years, is that there's really two issues that most affect well water quality, or drinking water quality for people with wells, and that is old construction. And I'm showing two examples here. We did a dug and bored well study in Illinois where we sampled over 100 dug and bored wells that are mostly these old brick wells, and they have a lot of issues. But there's a lot of wells that don't meet construction code today because they were drilled when there used to be a much less stringent well construction code, or even before well construction code was established in that state. The other issue is lack of well owner knowledge and education. We certainly have well owners who understand their water quality. They sample, they do everything they're supposed to. They know how their pump works. They maybe fix it themselves, all those things. But there's a lot of well owners who can't do those things and don't understand. And so we need to do a better job of trying to get that message out. And that's really, these two things are where we can focus and make the biggest difference, in my opinion, as far as the number of people who may be at risk of public health issues related to drinking water from a private well. And I guess that's my point. As far as poor construction, there's things we can do here. Well construction codes have changed significantly, and I say the last 30, it's more like 50 in some cases years. States that grandfather in wells that are already in place. So we still see wells in pits, and we still see hand dug wells that are still in use, like some of those I showed today. And they're not only an opportunity for surface contamination, especially a well in a pit, but they're also a safety hazard. So, back in the 50s and 60s, we saw when before that, people put wells in pits when they're in a cold climate because they didn't want their pipes to freeze. The pipe came straight out of the top of the well. So they stopped the well below the frost line, where in central Illinois that might be 3 feet. And so you just dug a pit and you put your cap 3 foot below land surface, and then you ran into the house. But those pits can flood. So if your well cap's not completely properly sealed, then you're putting surface water right into your well. A lot of times they're not properly covered, or covered with something that's strong enough to handle whatever weight might go on it. And so, you see where a tractor has ran over an old top of an old pit and it's caved it in, or somebody's fallen through. There's all these stories. And here's just two examples of old wells and what can happen. So this picture on the left is from the Washington State Department of Ecology. They are the agency in the state of Washington that regulates well drillers and well construction. And they have a blog, and this is actually like from 2013, when I followed their blog a little more closely. But there's a piece of plywood over this well. It's in a little well house, but there's a dozen problems here. One, you can see the gray matter that's around the outside of the well. That's likely old insulation that's just sitting there. It's just a piece of plywood over the well, which, she stepped on it and it broke this time and it killed her. But there's an old funnel there just laying there. That's probably to put oil in the pump. It's just a really bad situation. Anytime that you're doing any work with all that insulation sitting there, you're going to knock some into your well. It's just, your well should be something that you can't drop things into, as the bottom line. And the one on the left, or on the right, that's a goat. It's, you can see its ribs. It's, they put a piece of concrete tile for the upper 4 feet for an old brick lined well, and it wasn't covered. And yeah, this goat managed to fall in, and yeah, we've seen everything. We've heard, snakes, frogs, horses. I'll show you that in a minute. All those sorts of things. So what do you do if you have a well that's not properly constructed based on well code today? And you could probably have your county health department or local health district or even extension folks may come out and be able to tell you, what things might be best to do here. But you can, if it's a well in a pit, you can extend the pipe up above land surface and fill that in, with clay, install a pitless if you need to. Again, a pitless adapter is a device that allows you to still have your well cap all the way up above land surface, but it does a 90-degree turn for your pipe so that water is going into your house well below a frost line. And those started being used in the early 60s. Same thing for abandoned wells. Because we didn't require well logs until at least the 60s. In Illinois, it was 1968, or in the 80s for a lot of other states, or between that time. Some states, though, like New York, it was 2000 before they started requiring logs. So like in New York, they only have logs for probably 10% of all the wells that are actually out there in use, just because they didn't require logs until so it's so late in the game. So in most cases, there are many undocumented wells that aren't on file, and many of those aren't in use anymore, but they were never properly abandoned and sealed. So as an example, even for wells that are in use and the number of wells we have records for, I had 5 students spend a summer inventorying wells in 9 townships, so 9 36 square mile areas, and they found 1,708 wells, and we only had logs for 788 of those, less than half. Now, this was a rural area, a lot of farmsteads, so a lot of old homes, and that may skew that a little bit, but it's certainly a good example of what we don't know. And, many old farmsteads have an old dug well that then they put in a drilled well. They just kept the old dug well so that they could water the garden or whatever, or maybe even for livestock. But now a lot of those are unused, they're abandoned, and they're just a big safety hazard. So, and if you have one on your property and you're not using it, and you've got a piece of plywood over it or however you got it sealed, just remember that you're responsible there. Even if someone's not supposed to be on your property and they are on your property and they fall in and it kills them or they get hurt, you're likely going to be responsible. Or if someone or if you dump things down that well because you don't have another place to put it. And I'll be honest, my dad was that way with dumping stuff. And that's the way I grew up on a farm. Then if it contaminates the aquifer and it actually, water moves in the ground, it's always moving. And so depending on the flow direction, if it affects your neighbor's well, and people get sick or livestock get sick or whatever, again, if they can figure it out, you're going to be responsible. So the best thing to do is to seal those and properly seal them with, cement and clay, and follow the well code in your state to do so. And if you're in one of the few states that doesn't have a well code, which there are 2, then use from a neighboring state or use Illinois. It's a pretty good well code as far as what to do with abandoned wells, and ensures that you're not going to contaminate anything. The well is never going to be a safety hazard, all those sorts of things. Yeah, and here's some examples. The picture on the top, again, both of these pictures are from the Washington State Department of Ecology blog that I followed. And one is just, this horse fell in this well, they're trying to get it out. Whether it has broken legs or not, I don't remember. I don't think so. I think it actually was fine. And the one on the bottom is the more remarkable one. This guy in Sheldon, Washington was walking in his backyard and fell through a thin layer of soil, and there was an old abandoned well there that wasn't sealed. He fell 45 feet into the well, and when they pulled him out, he walked away unharmed. Amazing, actually. And then these others are all newspaper clippings from the 90s. And the third one is, if you're old enough, you remember Jessica McClure. She was a little girl who fell in a well in Texas. and CNN carried it live, and it took 18 hours to get her out. But some of these other folks weren't so lucky. You know, they died falling in a well, and they're from all over the state of Illinois. And so, you know, these things happen. They're out there. If you have one, you should seal it, is the bottom line. So a little bit about aquifers and aquatards. An aquifer, and this is I'm going to give you the definition, and then I'll explain it a little better. So an aquifer is a saturated geologic formation group or formations that yield water in a sufficient quantity to be a consequence as a source of supply. You would be surprised how scientists that are in this business have argued over what the definition of an aquifer is. And the way it's defined, you may be in an area where you only get 2 gallons a minute for your private well. And so you've had to go to extra lengths to try to make sure that you have enough water to use every day because there just isn't much water available. Well, to you, that's an aquifer still because it yields a sufficient quantity of water. But for a city, they couldn't use that same geologic unit that you're calling an aquifer as an aquifer because they can't get enough water for, you know, they might need 100 gallons a minute or 1,000 gallons a minute, and they're not going to get that. So the other side of that is an aquatard, which means it doesn't provide an ample quantity of water compared to an aquifer. And so typically, I mean, in general terms, an aquifer is either fractured bedrock or sand and gravel, and an aquatard is a clay, a silt, or a shale. Or glacial material sometimes is much more mixed up. It's got sand, clay, and silt all in it, and depending on the relative percentages of each of those, you know, if it's 80% sand, then it's likely an aquifer. If it's 80% silt and clay, then it's would be an aquatard. It means water can't move through it quick enough, and it can't leak enough water out of it to provide a water supply. Again, different users and uses will define what an aquifer is or isn't. And again, that's just the party line, if you will. It's not that practical for all of us to use every day. More common terms, you know what the aquifers are in your area, as well as where the layers of aquatards are. As far as confined versus unconfined, so an unconfined aquifer means it's not under pressure, so it has a free surface. So the best way to explain that is, you know, the wells that I showed today were all confined because the water level rose higher than the top of the actual aquifer unit. And in an unconfined system, the water is down in that aquifer somewhere. So the best way to explain it is, say you have a large glass of ice that represents your sand. If you pour some water in it and it's only half full, that's what an unconfined aquifer would look like. The water level's down in the sand somewhere or in the aquifer somewhere. It's not full, and then, you know, because it's got a cap on it, you know, it's not going up above the top of the aquifer. Whereas a confined aquifer, which we've looked at today, is where it's under pressure, which means it's greater than atmospheric pressure, and it's usually covered by something like an aquatard, or an aquaclude basically means it's a really tight aquatard and no water can move through it. So that water levels, when you put a well in, rise above the top of the aquifer, and that's artesian. So in our two examples today, both of those aquifers were artesian and both of those wells were artesian. There's a misconception that artesian means it's flowing, and artesian really just means that it's under pressure and it's above atmospheric, so water levels will rise above the top of the aquifer. So like in the one case, the water level was at 72 feet, even though the top of the aquifer was another 100 feet down. So there's enough pressure to push water up in that well 100 feet above the aquifer. Okay, so in an unconfined aquifer, the vadose zone, which is the unsaturated zone, this is all one type of material. Let's say it's all sand, and there's a water level down in the aquifer somewhere, and so that's unconfined. Where that little triangle is where the atmospheric pressure is equal, it's equal to atmospheric pressure. So there's no difference. You don't see any fluctuation there. If you have a confining layer like this aquatard that we put in, then depending on the pressure on that system, the lower aquifer that says confined aquifer, the water level rose up somewhere into that clay in that well, which means, so that's the water level. And then the unconfined aquifer above that, again, it's still at the same spot. It's the water table. So in this particular case, the unconfined aquifer has a higher water level than the confined aquifer. So water's actually moving slowly down through the confining layer into the confined aquifer. And again, water flows based on pressure. And the higher the water level, the higher the pressure. So water's trying to move downhill. What would happen if there were no change to the system and no water was added and none could leak out? Eventually enough water would go down through the aquitard into the confining aquifer until those pressures were equal and the water levels were the same in both. And we see that sometimes where there's connection. But because it's not, it's a dynamic system, there's rainfall, water's leaking out of the aquifers are being used, then this pressure difference usually is maintained over time. So in a confined aquifer, and again, those little dashed lines mean it's something that doesn't let water through. You can have a water level that's above the aquifer but below the water table, or you can have it that's above the water table, which means in this case, that clay layer that's in between the two on the previous example, water is going to be flowing up through it because the water level in the confined aquifer is higher than the water table aquifer. And you can have a flowing artesian well, which just means that where you're at on the landscape, there's enough pressure that when you put that well in, it actually flows out the top. So, and this can be, we have a couple areas in Illinois where this is the case. And we had a drought in 2012 and some of those wells stopped flowing. And the folks that lived there were pretty upset because they never had pumps before because they always had flowing water. Yeah, it's really interesting how that all works. So here's another example. And again, this is adapted from one of the Iowa resource that we had seen before. So what this also shows is, bedrock I said isn't flat. So these aquifers aren't flat. And so somewhere far off to the right, these aquifers both come to the surface, or the bottom one, the confined one, comes up to the surface and is recharged. And so because of that, when water wants to be flat, you can see the dashed line where the water level is on the well on the right that says artesian well. The water level's up above the confining layer. So that's under pressure, so it's artesian, but it's below land surface. So the water level maybe be 10 feet in that well below land surface. As you move lower on the landscape towards the stream, that deeper aquifer, now that water level is above where the top of the well is. And so when you drill that well, it's going to flow. And so you'd have to cap it if you wanted to protect it from having the water just running out all the time. Whereas the water table aquifer, which is above that, it's always discharging to the stream, so it never gets as high as where, the pressure of the deep aquifer might be. And it's all based on what's going on way off to the right. It could be miles or tens of miles or even 100 miles away, but pressure, is instantaneous. And so it's moving through that system pretty fast. And those differences in pressure are what drive water moving through an aquifer. So hopefully that makes sense. Here's another example, a real one. I mentioned before the deep sandstone, that's the St. Pete and Ironton Galesville in the Chicago area. So the dark blue on the right is Lake Michigan in Chicago. And DeKalb is where Northern Illinois University is. It's further west. I want to say it's about 40 miles west of Chicago. But you can see that the geology in the sandstone isn't level, which is the way geology is formed. It's all, I'm not a geologist, so I can't explain why, but it's all, there's a lot of differences. The red dashed line is the actual water level in each of the wells at each of these towns. So the lowest water level in that entire aquifer is at Elmhurst. The elevation is about 0, mean sea level, if you look at the graphs on the right, or on the vertical axis. So water's flowing from the very left side from DeKalb towards Elmhurst, but water's flowing from Chicago towards Elmhurst as well, because that's where there must be more drawdown there, whatever it's causing, the water levels are lowest. So even though it looks like water's flowing uphill from Chicago towards Elmhurst and DeKalb, that's what water does. It flows based on pressure. So it is flowing in both directions towards the center in this case. And we have water level information to document all that. And again, it's based on water use and how much drawdown there is. And I'll explain that more here in a second, or right now. So when you pump water out of a well, and if you look at the top where it says water table and it's got a dash line, and then with the pumping going on, it shows the darker colored blue. That's in the solid line, that's the water level near the well. So in an ideal situation where all the sand is the same, and it's uniform sand, and you start pumping a well, you form a cone of depression at the well. And depending on how hard you pump it, the deeper that cone of depression will go. So in our example, the static water level where the water table was around 460 mean sea level, and we're pumping it at whatever rate that causes the water level in the well to drop to 400. So as the water level drops in the well, water from the surrounding area starts trying to move toward the well to fill it in. Think of a bathtub. You know, that if you have a bathtub full of water, it's all flat. Water wants to be flat. It's at equal pressure all throughout the bathtub. If you pull the plug to drain it, all the water is running out. That's your well. And so all the water is moving towards that, trying to fill back in, but it can't because it keeps draining out. Well, same thing when you're pumping it out. And obviously your drain on your bathtub isn't in the center, but if it were, this is what it'd look like. You'd see a cone of depression around it that was circular and uniform. And so there's variations on that. If you have two wells pumping, then the area between the two doesn't have as much, the water levels drop there too, so more water's coming in from around the wells. And this is what that would look like when you have overlapping cones of depression. And a lot of times that, depending on the rate, that would make the water levels go down that much more in the middle, and depending on how long you pump. If you're near the edge of an aquifer, then there's no way for water to come in from that side. So you see more drawdown near the edge because there's no water there to fill back in the well. And so it has to take it from all the other pieces, and those keep filling up from a further distance. So it looks, if you look at the top picture, then that's what it looks like if you slice through it, and the bottom picture, we're looking down on it. Or on the other hand, if you're near a river that's connected to the aquifer, then it's a continuous source. The elevation of that river is 445. It's always going to be 445. I mean, depending on the size of the river and how hard you pump it, you can't pump enough water to actually affect the elevation of the river. It's just got too much water volume available. And so it muffles, if you will, or reduces the cone of depression between the two. And because it's a continuous source, water just keeps flowing from the river, and it's much more available than even through the aquifer. And you can see on the other side of the river, there's equal lines of elevation, 450, 460, 470 in the bottom picture. That's because, you know, as the land surface rises away from a river, water's running through the aquifer toward the river. It's its discharge point. And so it's always going to be the lowest value. Okay, one other thing, our State Geological Survey, and we're sister agencies, we work together. They develop an interactive map, and Illinois well logs are public records. And so anyone can come into our office and ask for their well log. They can get it free, or they can call us. We provide a PDF, or they can look it up through this GIS service. So they have this cool mapping thing, and I bring this up because I know there's, I just ran across one the other day from another state, and it basically looks identical with different colors to this one. And so I don't know if they all talk and they're all sharing code or what's going on, but this is a really handy online tool. And so you can, you know, if your well log's available in Illinois, you can find it here, or you can look and see if your state has one. But I'm in Champaign County, where the University of Illinois is. This is where we live. And so you can see there's the aquifer shown in this case. That's the Muhammad Aquifer. The Champaign-Urbana is kind of on the edge. But if I zoom in near the airport on the south side of Champaign-Urbana and click on a well, I clicked on one that says 269. But if you look at that little square, it says there's 2 of 3. So there's 3 wells that are at this location, which isn't totally unique. Sometimes they're used for different uses, whatever. But then if I click on that blue number, the API number, I get a generated log. So the Geological Survey not only enters the well information, but they also enter all of the geology, and they interpret it when they do that. And so you get this interpreted log, very detailed. And so one of the other logs that's part of the 3 logs that are at this location is a water well. And so it's a 3-inch casing, and it's old. It's from 1959. And the blue on here shows you that they've linked to the scanned image of the original log that we have at the water survey. And so now this will go back to the water survey. And when I click on it, I get this original log from 1959. But they didn't fill it out until 1968. I'm not sure what the story is there. But what I found interesting is when you look at number 15 on this one, it says that they have a 50-inch diameter concrete pit, 0 to 5 feet, and then 4-inch casing. It doesn't say it's 4-inch, does it? It's 3-inch. Actually, it says it on the other side. It's 3-inch casing from 4 foot to 162 feet. So they put in a concrete pit for this. This is so instead of a pitless adapter, this is before they were available. And it's a 3-inch well, which, and it's got a 3/4 horsepower motor on the pump, which these days most pumps are rated by how they're rated flow, gallons per minute. But it's just another well log that we have in our files. It's just it shows you how things have changed to some degree. And so, but this is all available from you in your home. You can search for this. Now, a lot of the water survey scanned images like this one are not in their system yet, but we do have most of our well logs scanned, or a lot of them, and folks can contact us. And I'm sure it's the same in a number of other states that have these same features. You can find your well log that way, and that's a really important issue. In Illinois, our county health departments are responsible for permitting and overseeing well construction. And then when the driller files the log, a copy comes to us. And so each county has their own set of records, which they're required to only keep for 10 years, which I still and will never understand why that law was put that way. But we keep them all and have records going back into the 1800s of wells in Illinois. So that's kind of the groundwater wells portion. I do want to talk a little bit about the private well class. It's 10 lessons, as I mentioned. You sign up, it sends you an email once a week for 10 weeks. It's a PDF. It's self-paced. You're on your own to look at it. We certainly encourage you to. Then we do these webinars to support those lessons, as well as give you a chance to ask questions, which like a few of you have today. And then we have other things to support it as well. Go to privatewellclass.org and you can see what's there. We also have an email address and a dedicated phone line. We take questions. We try to help people find answers in their local areas, no matter where it's at in the country. So this is the front page. You click on Take Our Free Class and it takes you to this page. All we ask for is your email address, your first name, and where do you live as a drop down by state and or not in the US. And that's partly for us counting beans for our sponsor. We need to be able to show that we're working with folks all over the country, and this is how we do that. And we certainly have. I think we have folks from at least 9 countries who've taken our class, as well as all 50 states and territories. So, but that's really what it's that simple. You'll get an email. There is a pretest that you do online. I think it's 9 questions. And the idea is you take the same test at the end, and hopefully you've got a higher score. And then we track that as well, just the scores, not who or whatever. But that way we can show that, people are actually learning something by going through these lessons. And then we have an evaluation at the end of that, just to say, hey, what would you like to see differently, or what could we do differently? We got some really good advice through that over the years. We've had over 11,000 people take our class in the last, I guess it's 6 years. So yeah, I just want to mention that it's available in Spanish. We're fortunate being at what I'll call a world-class university, that we had a Fulbright scholar from Columbia in civil engineering who was really up for the challenge of converting our class into Spanish. And so if you work in an area with a lot of native Spanish speakers, this is an option for them. For each lesson under our resource library, there are additional resources available. So the idea here is, if each lesson is 6 to 10 pages of text and figures, if that doesn't resonate with you, it was written such that it's like a conversation with you, and then you can go to these other resources that are all about the same topics. And there's a lot of good information, like the Raymond Lyle stuff in lesson 1. This is from Cornell in the 80s, or around 1990. Really well done, and still very, they really to the point and explain things in a really concise way. So there's a lot of those resources, and there's 10 of these, one for each lesson. And for instance, the first thing listed under number 2 there is the Michigan Flowing Well Handbook. Michigan was losing 28 million gallons of water a day to flowing wells, and so they passed a law requiring them all to be capped. And so that handbook it's got everything in it, ways to cap the well, the type of devices you need in order to keep the pressure and not lose the water. It's really worth looking at. It's pretty interesting. We do webinars like today. In August, our webinar was entitled, "Is My Water Safe to Drink?" They're on YouTube. We have a YouTube channel. So like the webinar today is recorded. Folks will be able to see that probably by early next week on our website, and they're all, again, publicly available and free. Specialty ones, like on funding and financing, that's probably one of the most common questions we get. And a lot of the calls we get are from folks where their well has gone bad or collapsed, or their pumps failed and they don't have the funding to replace it, and they call us to ask what to do. We refer them to this and to the USDA's program mostly. Unfortunately, there's not a lot of options for private well owners. That's another side of this, that if you're a private well owner and have a well, you're responsible for financing all those things, which, some people say, I like having a well because I don't have a water bill. Our take on that is, you should give yourself a water bill and build up a little fund, because eventually a pump's going to fail or something's going to go wrong, and then you'll have the money to do that, rather than having to try to come up with several $1,000s. Or, we had a colleague here at work whose well failed, and he had to put in a whole new well, and it was $11,000, and that's cheap compared to some places in the country. And then other ones we've done are related to specialty things like lead. Lead is a huge issue in premise plumbing. It not only affects community water supplies, which is where all the information is, but it affects any home that that was built before 1984, especially. But lead-free really wasn't lead-free until 2014. So if you have copper pipes with lead solder, that lead solder can be as much as 5% lead. And research like from Virginia Tech shows that even that amount of lead, given the right water chemistry, can cause lead issues in drinking water in a home. And so it's worth noting, we actually had a researcher from Virginia Tech participate in this webinar. Dr. Kelsey Piper, she's now at Northeastern, but there's a lot of good information that any homeowner with potential for lead pipes or galvanized pipes or copper pipes with lead solder should be aware of. We developed a page of resources for that. It's just privatewellclass.org/lead. And there's information here, especially for water filters and things like that. We have also these training videos, 16 of them, or there's 18 now, on special topics or individual topics like what should I know about a shared well? If you share a well with somebody, it's a lot bigger issue than most people realize. There's a lot of them in the country. Or how does my pressure tank work? Or what is a confined aquifer? Just individual topics are all 4 to 6 minutes long. Are probably this video or one is how does my pressure tank work are probably the most popular. I think the latter one I mentioned has had over 400,000 views. And it tells us that a lot of people have water pressure problems and don't necessarily understand. This is a little dated because these days now they're installing systems with a pump that runs at pressure. Instead of having a large pressure tank, you have a gallon or 2-gallon pressure tank, and then your pump kicks on when you need it, and how fast it runs. It's a variable speed drive, depends on how much water you're using, and it pumps hard enough to maintain a certain pressure. And so we see a lot of times now, older homes still have these large pressure tanks, but any new installations are going to these really small ones with a variable speed pump. And it guarantees that as long as there's enough water in the well, the pump will maintain the pressure when you need it. We started a podcast 3 years ago. We've had 3 seasons of that. There's 36 available. It's called the Drinking Water in Rural America podcast. We bring on folks like Brian Swistock's retired now, but he led Penn State's extension program for private wells for over 20 years. By far one of the smartest men I've ever met related to private well issues. Alan Wolf is the director of pediatrics at Harvard Medical School and Boston Children's Hospital. He works with special cases where sometimes those end up being private well issues. And so we had him on to talk about some of that stuff. Just not just private wells, but also small community wells, water systems. We have folks on both sides of that fence. If you're into podcasts, though, they're all players nationally, in most cases, and interesting folks you'd it's worth your time to meet. So our program overall is really about these things to help well owners understand why their well is important, why they need to understand how it works and what the issues are, and really all of that so they can help protect themselves from risk, because it's their responsibility. They need to understand that. It's not meant to overwhelm anyone. It's meant to say, listen, you can, the more you know about your well and how it works and water quality and the geology and your well log, all those things, and you sample so that you're in the know, the better off you're going to be, and the more available you're going to be to protect yourself from risk. There was a survey that folks in Minnesota Extension and also the other researchers from Wisconsin and Michigan, I think, they surveyed 2,700 people in all 3 states total, and like 1,600 responded, and 8% of those people said they didn't want to know what their water quality was. And I can't help those people. We need to help them understand why they do want to know, and they should understand, and when they should test, and some of those things. So okay, so we're going to go to the submitted questions, and again, Katie's taking your questions and putting those in a Google form that we're going to use in a little bit, but I'm going to go through some of the questions you asked today, obviously when you signed up, obviously, and all the questions that we got yesterday, I did not add any of those in. I couldn't get to them all, and so yeah, and we only have till 3. So first one is about groundwater management areas. Our district is classified as a groundwater management area. Do you have any information on this and any advice on how to explain this to residents? So there are GMAs, or in Illinois, they're called groundwater management zones in many states, and they all have a different purpose. Their exact function is really dependent on why they were developed. Sometimes they're formed by the state, and other times they're just a local jurisdiction or a county. So in general though, what they do is they're meant to help protect the quality and quantity of groundwater. So when they kick in, if they have any kind of actual regulatory authority or responsibility, it's due to a surface spill where there's a concern that it's a shallow aquifer, or it's an area that's got a high infiltration, so a spill is likely to get into the aquifer, or where you have limited resources, meaning not enough water to just unlimited use. And so they either manage pumpage or they're watching what's going on with the aquifer by measuring water levels and taking water quality samples, so that when they hit a trigger point, they know they have to then add some actual management and try to protect the system. And that's what's going on in Texas. They have management areas throughout the state, and each one has its own rules. I think I can't remember how many there are now, but there's a bunch. But everyone, like one, it's in a way, it's not a great system, because you may have two management areas right next to each other, and one has decided that they're going to have restrictions when the aquifer gets to 50% of its capacity, and the one right next door that's using the same aquifer may say 75% of capacity. And so then one of them is going to have restrictions while the other one doesn't, and then they could be within a mile of each other if they're right near that line. So I looked at Texas, Kansas, Washington, Illinois, and Minnesota. Minnesota's are done by their DNR, so it's a state agency. In Washington, the one I looked at was King County. They have 5 management areas just in their county, and they're more on the science and education side, from what I could gather. They're measuring water levels and taking water quality samples and providing data and outreach, and so that folks know what's going on. Water levels, if they change over time, so that if something's needed in the future, I guess that's probably something that would have to come up. But this question was open-ended in that I don't know where you live, and but you can look into it, and that's the point here. I found this fairly easily, and so but in general, that's what you'd want to tell the residents there, is just that they're really there to monitor water quantity and quality in order to ensure that there'll always be a viable resource there. Okay, when to test. How often is it necessary to test well water? So we suggest, and some of our other webinars, we go into this in a lot more detail. I'll just tell you now, it's worth looking at some of these questions in some of the other webinars that we have that are recorded. Coliform and bacteria annually, and I'm going to make it clear, I might have said this earlier, that those are considered surface constituents in the surface environment. And so if you find coliform or elevated nitrate, that means there's likely a pathway from the surface or near the surface into your well. And that's a problem. You need to identify why, because it just shouldn't be happening. So then we also suggest you test for inorganics and metals every 3 to 5 years. And I know I didn't provide a list here, but we have a list that we recommend. But in addition to the list we recommend, which is for a national audience, you need to ask your state health department, your local health district or county health department, your water quality folks, whether it's a DEQ or a water survey. If someone from Tazewell County called me, I'd say you definitely need to test for arsenic. I show an example sometimes of Rhode Island. About a third of the state has high beryllium in their groundwater, which isn't a common constituent anywhere that I know of, but it is in Rhode Island, and it has health effects, and has an MCL under the Safe Drinking Water Act. So you need to ask, and then anytime you open the well, or and if you've had to disinfect the well, then you should take a follow-up sample for coliform to be sure that it's safe. And anytime you've had an event, this is a picture from El Paso County, Colorado, after a forest fire. And you can see that aluminum well cap laying there next to the well, and all the burnt wiring. All that wiring stuff's dripping down in the well. Some of the aluminum may have dripped down in the well, or whatever those bolts were. But this went through a forest fire. And so if that well's ever even going to be usable, you obviously have to pull the pump and redo all the wiring and everything else. But you'd want to pump it and test it and make sure that it's even safe to drink. Tannins in well water. How worried should we be if we pick up tannins in well water, and should we test water after experiencing tannins? Luckily, tannins, although they makes the water a funny color, and it's got a little bit of yellow tint if it's just the right amount, and it looks kind of bad, but they're really just organic material from vegetation, and so they're not really harmful as far as health-wise. But again, they're an aesthetic problem. They have a color, they can have a taste that's an aftertaste, is what I understand. And it can smell musty, to make the water smell musty and stuff. One of the better documents is from the Water Systems Council they have this 3-page brochure on tannins and well water. It kind of explains a lot more detail what that is. You should be able to Google that and go to their well care information and just search for tannins, and you'll see it there. So this person wrote a really long question, and so I wrote summary because I'm summing it up. Nearby farmer applies liquid manure. Some of it flows overland through a swale onto his property near his well. His well is 150 feet deep. It tested fine, but it smells like manure sometimes. He just moved in. I would say recently moved in, and maybe it's been 6 or 9 months, but the house was abandoned for 10 years. And his plumber actually told him to use concentrated bleach in the well and then run it for 2 hours through an outside spigot to get it out. And that seemed to help. So the problem here is if the well tested fine, which, you know, I don't know what you tested for, but I'm assuming at least coliform and or nitrate, then it's not from the manure, because manure would cause it to have high, would have coliform and or high nitrate. I'd be really surprising if it didn't. So I don't think that's the issue. Really what I think the issue is a house that's stagnant for 10 years, water stagnant in all the lines. I would guess you have iron or sulfate reducing bacteria in your well, in your lines. It could be in everything. And so when you chlorinated your well, it may have helped reduce that because you've killed some of that bacteria. But I'm wondering if instead of a manure smell, it's actually not more of a rotten egg smell, because hydrogen sulfide is typically the off gas from those bacteria, and that's typically what we see. And you know, I grew up on a hog farm, so manure smells very different from a rotten egg smell, let me tell you. But once they've established in your home, it's really hard to get rid of. And if it really sat for 10 years, I don't know what you did when you moved in, but you know, it may need chlorinated a number of times, or you may need to just consider adding an inline chlorinator in your home so that you have permanent chlorine treatment, and that will likely eventually get rid of it. So, so the other things, adding the concentrated chlorine is a bad idea. You should, when you disinfect your well, you shouldn't just disinfect in the well and then run it through one line in your house. You need to disinfect your entire system. I showed earlier those additional materials that are available for each of the 10 lessons. If you go to lesson 10, there's a document from the Minnesota Department of Health that has instructions on shock chlorinating your well. Use that. It explains it very well, why you should mix it to, you know, 200 to 300 parts per million at most, or yeah. And you run it through every line in your home until you smell chlorine. You run it through your well and circulate it first. There's a lot of things that just pouring concentrated bleach down your well is a bad thing. One, it's an oxidant, so it's going to release metals into the water. And so, yeah, I think, you know, plumber didn't give you great advice as far as how to shock chlorinate your well. And it could be that it's in your line, in your home, just because it's set 10 years. And that's why I said shock whole house, use proper plan, use the Minnesota thing. And if you can't find it, email us and we'll send it to you. And the other question I had is, you know, what did you test for? When people tell me they tested and it's fine, sometimes that's just coliform and nitrate. And, you know, I can give you a number of stories where someone was mad because they bought a home after it, quote, tested fine, and come to find out they had arsenic at like 150 parts per billion when the standard's 10, because they only tested for coliform and nitrate. And so, you know, knowing what you tested for would help too. And again, if you email us, we will certainly get back to you and provide you that information. How do I flood protect my well? Well, if your well is in an area that's a floodplain, which this is, those trees are along a small stream, the only thing you can do is extend the casing so that it's above the flood level. In this case, this well is 9 feet high, and they did that on purpose because this is the only place where they could get water, is in the sand and gravel alluvial sands along the stream down in the floodplain. And by putting the casing, solid steel casing, up to 9 feet, they could guarantee that water would never breach the top of the well. If you're not in this situation, but you're just, maybe it's a lower spot on the landscape, or it's a low area in your yard where water tends to pond when there's heavy rainstorm, then the thing to do is to raise the ground up around it. A best practice is to have mounded soil around your well so that water's running off in every direction. And, well code requires in most states it'd be at least 12 inches, sometimes as much as 24 inches above land surface. And that's really why. So if there's shallow ponding because of a heavy downpour, it's not going to breach the top of the well. And that's really all you can do that I can, it's common issues. Even a sealed well like this one still has a vent, right? That well cap, it's got a rubber seal. It's completely, it's a sealed well cap, but it's still got a vent, and because of that, you don't want that overtopped with water. They're not meant to be completely waterproof. Can a nearby plant that's opening deplete the local aquifers and wells of residential areas without legally requesting approval or permission from the landowners? This is very dependent on the state you live in and what laws you actually have. And I don't know what you know about the plant, but knowing how much water they're actually going to pump and what aquifer it's in will make a big difference. I mentioned the Mahomet aquifer near Champaign, where I live. That aquifer goes almost across half the state, and it can sustain tens of millions of gallons of pumpage from a plant, which I can't think of a plant that would ever use that much water. Even an ethanol plant's using 1 to 2 million gallons a day. But there's a lot of details here missing, right? Was there an environmental impact statement done? For instance, how'd they get permits to even put the plant there? What's the governing law in your state? So out west, it's first in right. You have water rights depending on who has a land water right for every parcel of land, out west. Whereas in Illinois, it's the law of reasonable use, which unfortunately means that if someone were to put in a high capacity use near you and your well goes dry, you have to be able to prove that and take them to court, because there's no other law or liability there, and you have to prove it. And so, not knowing those things or what state you're in, you need to become more informed before understanding. I know in a lot of cases, those are done like at the county level or some other kind of district level. And so it may be that they did all the right things and got permits and it was approved. And, there's supposed to be a public notice for most of those things. But again, laws are different everywhere. And so you need to find out all those things first before you understand where this can be a problem. What I would recommend, though, for you and your neighbors that have a private well is to protect yourself in case there is a high capacity use that affects your water. You should have a legally binding water level done, either by a professional licensed driller or contractor, or talk to your state about what information would be admissible if you had a complaint, and measure your water level, and so that this is what the water level is in my well, and here's my log to show what geology we're in, and so you can show it's in the same aquifer as this plant, and then maybe do that once a year and see what happens. It will cost you a little money, but it'll protect your well and your water use from anything happening. Does water from bedrock usually taste bad? So, there's no way to answer that question. Really, groundwater is affected by the mineralogy and the materials that make up the aquifer, whether it's bedrock or sand and gravel, whatever's there. And the second thing would be if there's any influence from the surface, how fast it gets recharged. There's no generic understanding that bedrock water tastes bad, is the bottom line. Any aquifer can taste different than any other one. the water in it, I mean. And the good news is we do have treatment like granular activated carbon filters that can remove a lot of the taste and odor issues, if there are any. You know, my brother-in-law farms up in northwestern Illinois, and their bedrock aquifer has sulfur in it. It's not caused by bacteria, they just have sulfur. And so we get hydrogen sulfide that comes out of his taps. When you take a shower, the water feels slimy. He's gotten used to it. I'll never get used to it. And it's just the natural water quality there. And so it really just, you know, I've never seen that anywhere else that bad. And so it really just depends on where you're at. There's a community between here and where my mom lives that I don't even like the fountain drinks from the gas station because the way they treat their water. And that's a community water supply. So, you know, it's different everywhere. And, you know, it's what, yeah, I guess the answer is no, is the bottom line. What are some homeowner options for arsenic treatment? So we also got asked about tannins and a few other things today. And so what I want to point out, this came out a year or two ago. Minnesota Department of Health has this guide called Home Water Treatment. It's the most comprehensive thing that I found. It's unbiased, it's by their health department, and it's free to everyone. This is the link. You can ask us for it later, or you can look it up. You can just Google MN Home Water Treatment, and this is going to be one of the first 2 or 3 links. But this document is amazing. And when you're talking about water treatment and dealing with water quality issues, it tells you things that are important. Like if you're going to buy a treatment device to treat anything, make sure it has one of these labels: the NSF, a National Sanitation Foundation label, the gold seal from the Water Quality Association, or the Certified Water Quality UL label. That means it's been tested by a third-party certifier, and that treatment device is going to work the way it's supposed to and actually take out the things that it says it does. So for instance, if you're going to buy an RO system and you have one that's $200 and one that's $800, and then maybe there's some that are, you know, up to $2,000, I guarantee you the $200 one is not going to have been tested, but the $800 one has. And you may buy a device that doesn't actually do what it's supposed to do if you don't go through and make sure it's certified. And that's just a good best practice. But this document, you can look by contaminant. So we had several questions about color and taste. We had a question about arsenic and also hydrogen sulfide. So then it shows you which devices typically work. So for arsenic, the most common 2 types of treatment are the first one listed there: absorptive media filtration, and RO, reverse osmosis, which is the last one on that line with the black dot. The most common way to treat those. And then as you look at those, they've put together exactly what each of these things do, how much they cost, point of use versus point of entry. If you're not familiar with that, I would be very skeptical of anyone trying to sell you a point of entry device. That means it treats your whole house. It's like your water softener. It's at the very beginning in your basement or where your treatment stuff is, and it treats every drop of water going through your home, from showers to whatever. Arsenic, for instance, is not a dermal issue. It's not an inhalation issue. It's a drinking issue. You only need a device at your kitchen tap for cooking and drinking for arsenic. And buying a whole house device, you can see the difference there from 300 to 700 versus 2400 to 4500. It's a huge difference, and also wastes a lot of water. So you know, but it lists both, which is great, and the pros and cons of each. As we go down through this, carbon filters I mentioned for hydrogen sulfide for that color, taste, and odor, and then down at the bottom is RO again. There are other ways. Some of them are more expensive. Like it says for ozonation and filtration, call a water treatment professional to get a quote. It's because it's just not used that often. Ozone's a little more difficult to work with. It costs a lot to run. And so RO is very common. And again, if you look at RO, the difference between a point of use device at your kitchen tap versus a point of entry device is astounding. It's almost, it's 10 times, right? And so there's really no reason to do that. And RO is it's a membrane, so anything that's too big to fit through the membrane doesn't go through, and it takes out a lot of things. Yeah. Is concrete harmful? So this is a question I've never had before. So they had a well drilled, and they were 10 to 12 feet from their old well that had collapsed. So they needed to put in a new one. So then after they did that, the driller was using the new well for a water supply to mix concrete and fill up the old well. Well, pumping the new well after they started putting concrete in the old well caused concrete to get in the new well. And so he then pumped the new well for 2 days before and got it to run clear. And he says running the pump full and on into our yard for 2 days. And so their question is there a concern? I researched this quite heavily, and I couldn't find anything specific about this issue. Certainly ingesting actual concrete is a different animal, and that's bad. But if it's running clear and they ran it for 2 days, I really don't, from what I've read, I believe that clearing out all the concrete in the system is going to eliminate any issues you might have. I don't think you find anything. So, and I understand, I left out here the health department wasn't interested in even dealing with it, and I get that. It's just not something you ever see, right? I guess if it were me, I would have considered not having my well that close to my old well. I understand there's reasons for that too, the water line to the house, all that stuff. But yeah, I can't think of anything. Groundwater is always moving, so it's moving off site, even as we speak, right? It's moving. When we looked at the very beginning, we talked about water flowing as much as 3 feet a day to 300 feet a day, depending on the aquifer. I mean, water is moving into the ground. It's moving away from your house and your well. And so, it's different water tomorrow than it was today. I just, I'm not a health professional, so maybe contact the state health department, the Illinois Department of Public Health. I think you were in Illinois, as I recall. But I cannot think of a way that it would actually be an issue. So, I mean, and that's, yeah, for me personally, I wouldn't have any worries, but that's me personally. Saltwater intrusion. So I supervise a well construction program for a county in the coastal plain region that has over 45,000 wells. Do you have any strategies for dealing with saltwater intrusion? The problem has increased in our area over the last decade. So this isn't really a well problem for the private well class per se, but I'm a groundwater hydrologist at the State Water Survey. We do a lot of this kind of not saltwater intrusion work, but aquifer work, and including artificial recharge. Some of our guys are into. It's really an aquifer management issue. The idea is you have to keep the water level in the freshwater aquifer above the water level in the saltwater that's getting in the ground, so that it's pushing, the freshwater is pushing on the saltwater to keep it in place, versus if the water level is lower in the freshwater aquifer, then saltwater is going to move in. There's examples of this, providing artificial recharge. The best one is Orange County. If you look up Orange County aquifer, probably just that. They input 100 to 130 million gallons of water a day through these settling basins that are sand into their aquifer. And they're actually treating tertiary treatment for their wastewater for water reuse. It's called indirect water reuse. And they're putting all that back into the ground and letting it infiltrate just to keep the water levels high enough so that salt water doesn't intrude, because they're pumping a lot of water every day out of that aquifer. But as far as you and what you can do, that's a much bigger animal and more than a county program probably. It's something the state would be involved in and all those things. I encourage you to look that up, but really the best thing you can do is provide advice to your well owners. If this has been becoming a problem over the last decade, you're not going to solve it individually. and it sounds like it's going to happen. And unfortunately, as sea level rises and we have more people moving to the coast and are using groundwater levels are going to go down, and it's probably not going to change. It's going to get worse. And so really they can consider treating their water for removing sodium chloride, sodium and chloride, or find out if there may be a deeper aquifer. In some cases, everyone's drilling into the shallow alluvial sand because it's right there and the water quality is good and all those things. But it turns out if you drill the 300 feet into the bedrock, there's a protected freshwater source that is a great water supply. Now, obviously, that's not a great option either if I'm the person that has to drill a 300-foot well and pay for it. But that's where they're at, and it's just the way it is with the way folks are moving to the coasts and all that. The other thing to consider, I know where we have water quality problems in Illinois, like in the karst area, Pike County I mentioned earlier, they received government funding and put in a rural water district. And so they ran lines on all the county roads and hooked every home up to city water basically. And so there's a rural water district there now that covers like 85% of the homes in the county. And so it's all city water, if you will. It's treated. They have a water operator. They're all part of a public water system, which isn't ideal either necessarily. But if you have 45,000 wells, that sounds like a fairly high density, and maybe a public water supply makes sense. And especially if there's saltwater intrusion issues that are getting worse, I think I'm sure some public water supply that's already there could make a great case for expanding into that area. Those are the only options that I know of, unfortunately. Can we see pictures of pitless adapters and what is their purpose? So in the early 60s, I mentioned all these wells and pits. They developed this device that locks in place and connects to your discharge line to your house, so that you can pull out your pump, and also you don't have to have your pipe come to the surface, and it's what's called a pitless adapter. And so it allows you to have an adapter that basically, as your water comes up from your pump, it can do that 90 degrees and head towards your house. But this whole device can be pulled out so that you can pull your pump. And so its purpose is to not need a pit for your well when you're in an area where you have a winter frost line, freezing ground, like in Illinois, Minnesota, anywhere up north. And so that's really their purpose. You don't need one of these if you're in Arizona. We see places where it's warm all year where the pressure tank's sitting out next to the well outside, because they can. But if you're in a cold climate, pitless adapter removes the need for a pit. That's the bottom line. And you can see the frost line shown on here. And I didn't put it on here, and I should have, but this came from the Midwest Plan Service. They graciously allowed us to use this diagram. It's a consortium of 12 universities, which Illinois is one of, but they have a lot of really cool documents for rural folks and understanding, how to size your pump from, you name it, everything. Okay, so we had a lot of questions this time that were really not for me. I'm a groundwater hydrologist. I know a lot about private wells, but I've never installed treatment equipment or pressure tanks or ran the electrical lines. And so, when you say, can you discuss pumps, appropriate size? I understand, turbine pumps that are used for irrigation wells and pumps that are sized for a non-community and private wells. They're typically between half a horsepower and 1.5 or 2 horsepower, and that corresponds to, it depends on how deep you have to put your pump for one, and then how far you're pumping it, and how much pressure you need. And so, someone else asked about getting into pump curves and stuff like that. I did that in college, but I don't do that today. And so these other two questions, what kind of well casing joints do you see specified or used? I understand we have some drillers in our audience today, and when you get that much into the weeds as a driller, I'm not helpful. And, I would have to go ask a driller. And so that's the thing I'd bring up, when I go to my state association meeting, if there's an opportunity. And the same with going through the electrical wiring. Someone asked if we would follow the electrical wiring from the breaker box to the junction box at the well. That's not our capability. And as far as what size of pressure tank do I need, I mentioned earlier that they're going to these 1 and 2 gallon pressure tanks and using the pump as the pressure device. I know there's a lot of folks with older systems. It depends on how much water you use. Is there 2 stories or 3 stories? There's a number of things, but you're better off talking to an installer who does this every day to get that information. And there were several questions I didn't list here that were similar, things that are, beyond what would help a homeowner per se. How can I best have my well casing inspected? I think it's cracked. So really the best way to do that would be a downhole camera. And that's really the best way to identify if there's a crack in your well. And what matters, well, first of all, I'm curious why you think it's cracked. If it's PVC and you hit it with a mower, or somebody, bumped it with a car, or, that's one thing. But, there's generally a reason. Or if there's a large tree nearby, the roots are eventually going to go around that well and crack it. But, the important thing is if it is cracked anywhere, especially near the surface or in the water table, then that's certainly going to be a source of contamination. So if you really have reason to believe that there's a crack in the well, you should find out for sure. And I know there's a question about liners, which I wasn't going to answer today, but if you do have a crack in your well, that's one reason why you'd install a liner to basically close off that crack. And, if you have a crack just 2 feet below land surface, you put a liner that's 5 foot in and seal it. Now you've prevented that crack from affecting the inside of your well. What are some recommended well construction annular seal packing filtration materials and depths near within 500 feet to 3,000 feet of fuel contaminated site? So in every state but 2, there's well construction code that dictates how you drill your well. You can do more than that, but the materials, how you grout it, what kind of casing you use are all dictated by construction code. What really matters for you here is understanding your geology, and as far as the depth of each geologic formation, where it's finished, or where you're going to finish your well, and where your water is coming from. So if there's a geologic barrier, which is a poor way to say an aquitard, like shale or clay, between the contamination at the surface and where your water is going to be coming from, and you're going to case through that, then there's likely not going to be an issue. But if it's all sandy soils and your well's a shallow sand point, or it's going to be in the same unit, then you really need to know the groundwater flow direction to understand if it's potential or not. If you're at a Superfund site and the flow direction is north, that means if your well is north of that place, there's risk. If it's south of it, there's likely not much risk, because any flow is going to be away from your well. And so understanding that is important. And I said, is the site being remediated? What I really want to ask is, how big of an issue is this? Is this on your farm and you had a small spill, had a gas tank from an old tractor that rusted out? Or is it, there's a real site here that needs to be taken care of, and it's got there's a large chance that it's going to affect an area and have a plume. All those things matter. How often, okay, so the bottom line here is this person has a well from the 70s and it's not used much now. No occupancy for months, seasons, and years. Hopefully, if you're on this still, you understand that, like the house that was dormant for 10 years, that's a real problem. So if you really want to know what's the minimum to pump it so that you can keep it clean, so when you have people come in, or if livestock are going to use it, none of those things are going to work. The bottom line is you really need to follow guidance for whenever the wells, before the system's used, it should be, there's startup and shutdown procedures for seasonal systems. The one we try to recommend to people is from the Washington State Department of Health, and it's also listed in our resources. It's under lesson 5. And so I would go there and look at their website. But you need to turn the power off. There's a lot of things to do, because if you have stagnant water that's sitting there for years, then there's likely going to be bacteria formation. It's just no way around it. The difference between a public water supply and a private well is that public water systems require chlorine residual in their distribution system to every home. Excuse me. But private wells aren't chlorinated. That's the bottom line. I just realized how late it is. I apologize. For those of you that are still around, I appreciate it. Let me get rid of this and bring over this and make it full screen. Can you see that, Katie?
Yep, it looks great, Steve.
Okay. Oh, wow. I'm just going to read this quietly real quick. So you have a well that pumped 20 gallons a minute in 1999. Yeah. I don't know that I do have any thoughts here. This isn't a typical issue. I'm assuming it's a bedrock well. Did you say that somewhere here? Let's see. Yeah, I guess the only thought I have is, assuming you don't have 225 feet of casing and it's a bedrock well, it could be that one of the shallower fractures, which fractures typically there's more of, and there's fewer as you go deeper into bedrock, may have been the water supply. And because of development or other uses or just lack of recharge, now that the fractures that were providing most of the water aren't there anymore or don't have water in them. And so you're down to those that are, yeah, my water zone is right at the bottom of the well. Yeah, and so it's certainly possible if it's a bedrock well that you're going to identify new fractures. It doesn't mean that they will. It's that's the only chance. That's the only chance you have. But I know even in Illinois we have we know where there's some very large fractures that show up. You can even find them looking at certain types of surface images, and it's an irrigated area. And if you hit the fracture, you can pump 1,000 gallons a minute, and if you miss it, you might get 25 gallons a minute. And so that's the risk. But drilling isn't an exact science. Geology is complicated, and so I wish you luck. I don't know that I have any other thoughts other than there's no guarantees whenever you're doing that work. So I just talked to someone last week. Yeah, I'm not going to discourage you, but it's really just dependent on hitting the right fractures. So what's the best system to remove hydrogen sulfate odor? I think I answered that question, and I would look at the Minnesota guide. There's several ways you can remove that, but for that, one of the things that we typically would recommend, which we're not treatment experts here either, but you need to aerate it before it comes in the house. So a lot of times you'll have 2 tanks. You have a tank that it goes into that's got a free surface and a vent, and all the hydrogen sulfide can bleed off. And then you pump that into a pressure tank or into your system from there. And so, it's basically aeration to get rid of it. And yeah, I would talk to a treatment professional, and you can get a list of those through the Water Quality Association on their website. They have a page where they also have a training program where you go through their program and you get a certificate saying that, you've met these criteria, blah, blah, blah. But then you can look at a list of those folks and put in your zip code, and it'll tell you who's nearby you, and you can call somebody from there. That's one way to get to a treatment provider. Is it use of the targeted aquifer water, or the fact that multiple small aquifers were drilled through that contributes to lowering of the water table and subsequent drying up of streams and rivers? Is there a way to plug small aquifers that are drilled through that are not targeted? Well, in a bedrock situation, usually it's all open hole and all the aquifers contribute, unless someone has a foresight of knowing which aquifer they want to use. Maybe there's water quality differences, so they actually case through some of the rock that they, quote, didn't need to. And we do see that. Matter of fact, the other problem where you don't do that, we're seeing issues in the Chicago area with those deep sandstones because they're open to both. One is draining into the other, and so the wells that are in the upper one, some of those are starting to have water problems because the water is draining into the lower one because of those connections where the well bores are. The only way to plug it is to put casing through it, and in a bedrock sense. And in the sand and gravel thing, you know, that doesn't happen. You'd have to case through the sand and gravel, or it's gonna cave in your well. So, do screens in sand and gravel always need gravel filter packs? That's the best practice. You know, the idea is you're trying to prevent sand from getting in your well. And so even if you have a fairly fine size screen, there's going to be fine sand in a natural sand and gravel aquifer. There just always is. It's not totally uniform like gravel pack is. And so you can use a gravel pack that's just large enough not to go through the screen. That's going to trap a lot of those more fine sands. And it's certainly the best idea. Because, you know, if you start pumping sand, you know, it wears out your pump. It can even wear out the pipes in your home. You know, I have a gentleman I worked with south of town here who had galvanized pipes, and all of a sudden he had a leak, and turned out he was pumping sand and it scoured an elbow, and it was just paper thin until it started leaking. And so, you know, sand's hard on any kind of equipment. It's sandblasting, right? So, yeah. So is a 10-gallon pressure tank small? Yes, and in the old style, if you will, but because it means you know your pump's going to have to kick on and keep up a lot sooner, and if you have a 100-gallon tank or larger. What it typically means, and again, I'm not an expert here, is that if you have a tank that small, it may be that your system's relying on your pump more than the pressure tank. I talked to the person who installed that. So, because I don't know of any tanks that are only 10 gallons that are not part of a system where the pump can kick on and keep the pressure up for the system. I'm closing on a home with a well and know very little about them. Are there recognized filtration systems if you do not like the taste of your water? Yeah, I mean, that's what granular activated carbon filters are for, a lot of times for taste. I would look online. Again, I would just make sure you use one that's been tested by one of those certification bodies. So you should sign up for a class and go through all that. Lesson 10 is all about treatment and what to look out for, and what to recognize. And you can always call us if you have questions too. So that's partly what we're here for. What steps do you think a homeowner should take that has E. coli contamination if you are unsure of where the contamination is coming from? The water level is at 370 feet. So E. coli is a fecal coliform, and having it means it's not about your water level or how deep your well is per se. It's about meaning that somewhere near the surface, something could have got in your well. It honestly could have been something like the well was opened for some reason and something got in. or where did you test from? We just had a colleague who was sampling outside spigots, and they ran into a fair amount of coliform and a couple E. coli hits. That could be that outside spigot has bacteria on the inside of it, and it's not in the home at all, right? And so I'm assuming you tested at your kitchen tap. I mean, the first thing to do is to shock chlorinate your whole system. And, I'd use the Minnesota guide I mentioned in lesson 10 to do that. And then test again and see if it took care of it. And if not, then you want to start looking at what the possibilities might be, whether it's a well cap, whether there's a breach in your well. Yeah, if it's 300, if the water is that deep and you have solid casing, then it obviously doesn't seem likely to be like a livestock thing or a septic thing. Yeah, that's unusual. So that's where I would start. So several years ago, my neighborhood was affected by a historic abrupt flood. We lived slightly uphill from where the water made a path, but even with sandbags, oh my, floodwaters were approximately 30 feet from our well. We had tested, but how long after the flood should one keep testing, like monthly intervals, or does it annually suffice? If it didn't reach your well, here I would ask, how deep is your well? What type of well do you have? I mean, if you have an old dug well, then if, coliform and E. coli are at the surface, but they don't exist long-term in groundwater per se. And so I wouldn't think that, yeah, it shouldn't, especially several years now, there should be no issue either way. Several years ago, if your well's tested negative for bacteria now, then I would just stick with a 1-year schedule. So, okay, I went way long and I apologize. Thank you for those who stuck around. And yeah, if you have any other questions, here's the information. There's our email address. And as well, if you're looking for CEs, that's the email address to reach us at. All right, thank you and take care. Oh yeah, look at that. Timeout. We did a webinar for our other program, the wateroperator.org program. And so Katie just caught that still was on there. It's info@privatewellclass.org. So, all right, take care.